Okay, so what I want to do to help you guys for the upcoming quiz is briefly review flux and then show how to apply Gauss's law with flux to a couple of common types of problems. So some of this will be partly review. Please speed forward through whatever you already know. So flux is this idea that we take an area, and this is meant to be sort of, this drawing here is meant to be sort of a little panel you might think of, like an area, like just a piece of paper you're holding up in a three-dimensional space, whatever. The blue lines represent the electric field across this area. I've shown them basically all pointing in the same direction. That's going to be important to us, but these just show that it could be, you have electric fields. You have an electric field at all of these points. So at all of these points, there's a different electric field vector, or there might be a different electric field vector. And then finally, you have this red vector, n hat, which is a normal vector to the surface, and the hat means it's got a unit length. So its length is 1. Its magnitude is 1. It has no units on it. It's perpendicular. Basically, the n hat vector is there to tell you which direction the surface is facing at any time. So the surface is sort of facing in the direction that n hat is going. So let me then tell you what flux is. This is all review. That's why I'm sort of speeding through it. Flux then is, if you want to do this in the fully rigid calculus form, it's a surface integral of the electric field vector dotted with n hat over this entire area. That's what this means. This means essentially you're taking E and dotting it with n hat at every point on the area to find little itty bitty pieces of flux everywhere. And then you're doing an infinite sum of all these little tiny, infinitely small pieces of flux you get. That's what the integral of dA means. Until you get to multivariable calculus, you really will not use this. Or now, there's a much simpler case we can make use of here, and this is generally where most of the easily solvable and interesting uses of Gauss's law come from. So, when this product here, this dot product between the electric vector and n hat, your normal vector, is constant over the entire surface A. Okay, so when E dot n is the same everywhere, then what you get is, instead of having to integrate, you just take E dot n hat. It doesn't matter where you take it because, like I said, it's the same everywhere. And then you multiply that by your area. And that will give you the flux for this entire area. But this only works, like I said, if this is constant, this quantity in here. So flux is kind of a hard idea to get a handle on intuitively. You can sort of say, if you take this same area we're looking at here, area A, okay, and then you take the field everywhere and sort of let that push it out. So sort of let it push through the area and make a little volume. So I'm drawing the field. In this case, I've got the same field everywhere. So I'm drawing where the field is going at each of these 4 corners. Okay, so it's always going sort of inward. This is bottom one. There we go. So and then what you do is you take, I'm going to use light blue here. You take and you sort of draw you sort of make this into a 3-dimensional shape. So this is what you call a parallelepiped. This is a flat surface here. There's another flat surface here, basically the same shape, and then it's sort of pushed through and it's got some thickness. And it's the volume of this parallelepiped. So flux is the volume of this. And what's the volume of that? Well, to get the volume for a parallelepiped, what you want to do is take the area of the base and then multiply it by the height. The height is the perpendicular distance between these guys. So this distance here, h, we can call it, is the height. So in this case, phi equals height of that thing times the area of the base. Okay, so to be clear, we're using the same. This is really the same thing as down here. So there you go. And this is, technically you would have to take this at different points and integrate. But so we're doing the case where it's constant, where your E is pointing in the same direction everywhere and your surface is flat. So that h there. So again, this is an E vector, right? And if we draw a normal parallel to your original surface, so there's your n hat, which is perpendicular to your little surface, then the length of h here is going to be the dot product of E and n hat, okay? Because this angle in here, we call that theta, okay? So call that angle in there. Actually, I'll do it in purple here, okay? So theta in there, theta is, well, let me put it this way: the cosine of theta is going to be the adjacent side of this triangle, which is h over the magnitude of E. So h over E. And what that gets us then is that h equals E times cosine of theta. And how do you get that cosine there? Well, you take the dot product of E and n hat, because this green line is going the same direction as n hat, right? So this just equals E dot n hat. Okay? And that's where you get, so now you know h is equal to E dot n hat, you plug that in here, and that's how you get that your flux is equal to this. So that's kind of, sort of a way of thinking about it. And you can see how, like, if the flux was stronger, then you'd, or sorry, if the field was stronger, then you'd have more flux. And if the field is pointing, the more the field is pointing perpendicular to the surface, the more flux you'll have. And so you can imagine, say, you know, you have this say this is a horizontal sheet. I'm sort of trying to draw in 3 dimensions. And say the flux is like that, or sorry, the field is like that. So the field is always going up through the sheet. This is going to be a lot of flux. A lot of flux here, okay? On the other hand, you have, say, a sheet like this, and say your flux is all going this way, you know, it's all parallel to the sheet, then you're going to have no flux. And so that's sort of the idea, because this, and you can see here how this dot product, if this is your, so let me make it clear again, these blue vectors are the electric field. I'm trying to consistently use blue for electric field so that you can sort of keep these consistent. And then, you know, n hat is your normal vector there. You can see how here, you know, electric field dot n hat is going to have, you know, these are pointing in the same direction. So the dot product is just going to be the magnitude of the electric field, dot, you know, times the magnitude of n hat. N hat always is magnitude 1. So the flux through here is just going to be your magnitude of your electric field times the area. On the other hand, here, this dot product is going to, they're perpendicular, so this dot product is going to be 0. So if you have an electric field going, you know, parallel to your area, there's going to be no flux there. And you can kind of see that because the electric field isn't punching through your surface here. Remember here we sort of said it was a measure of how much your field is punching through the surface. And here you have to imagine it has to be pushing, you know, sideways through the surface in order to create this volume here. So here it's not punching sideways through this, or it's not punching, you know, this way would be through the surface, and it's not punching that way. So it's 0, but here it is punching that way. So you got a big amount of flux for that. Let's see where I am now. Okay, it's almost, we're almost up 10 minutes, but I'm going to go ahead and tie this into Gauss's law. So the idea here then, I'm going to leave the, let's see, so I am going to cut this stuff out. So get it now if you want it. Haha. But I want to do Gauss's law now. Gauss's law says, come on, where's my button? There we go. All right. Gauss's law says, and I'm not going to prove it here, but Gauss's law says that if a closed surface around a collection of charges, so say this is our charge Q1, this is Q2, this is Q3, and we have other charges, blah, 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 a whole bunch of charges, you know, distributed however you want. And you draw a closed surface around all these charges. So you have to imagine that in 3D, this is not just a line I'm drawing, it's actually a closed surface. So it comes out towards you and goes out behind the page and just envelops all these charges. So it's a closed surface that is wrapped around all these charges, no holes in it, no way to escape. So for Gauss's law, so this is a closed surface. Okay. Then Gauss's law says that the total flux through the closed surface, so total flux through the entire closed surface, is going to be the sum of all the charges. Actually, let me do that smaller. Okay, the sum of all the charges. Okay, which is also sometimes referred to as the net charge. You can do it either way. The sum of all the charges. Actually, probably better just to write QNet because it's not all, you're not always summing discrete charges. Is the net charge inside the surface. So it's the sum of all these charges. If you have some positives and negatives, they cancel out. If you have all positives, they add up to bigger positive, etc. Okay, times 4 pi k. Or the other way this is written, and this k here is just your ordinary friendly 9 times 10 to the ninth for SI units. It's the k from Coulomb's law, etc. But the other way this is written is q over epsilon naught. And so these two guys, let me do these. I'll do these in orange. Okay. So k here and epsilon naught here. I'm going to take these guys out. Okay. Explain what they are up here. So k is your old, from Coulomb's law and everything. It's 8.99 times 10 to the ninth, and the units are, oh boy, let's see. So Newton meter squared per Coulomb squared. Okay, and then epsilon naught is just another way of doing this, and it is 8.85 times 10 to the minus 12, and it's got the inverted units from K, so it's going to be Coulomb squared over Newton's dot meter squared. And the relationship between these two guys, really did not plan this well. The relationship between these two guys is basically epsilon naught and 4 pi k are almost reciprocals of each other. So k equals 1 over 4 pi epsilon naught. And this is equivalent to saying that epsilon naught is 1 over 4 pi k. So you can go either way. So either one of these is valid because k and epsilon naught are really just ways of expressing the same, universal constant value. K is called Coulomb's constant, and it's used for Coulomb forces. Epsilon naught is called the permittivity of free space, and it relates to how flux flows, how flux occurs around a charge, that kind of thing. But you can use either one. Either one of these forms is perfectly correct, and they are in fact the same because k is 1 over 4 pi epsilon naught. So what people usually do in practice is they sort of, if you're deriving a solution to something and you have, like, say, when you're calculating your flux, you get like a pi in there, then you use this version so you can cancel the pi's out, or if you don't get a pi, then you use this. Basically what I'm saying is people pick whichever one is easier to write. Okay, and so what Gauss's law says is that when you have this closed shape, any kind of closed surface around a collection of charges, or some net charge, the total flux through that surface, no matter what shape it is, no matter how big it is, no matter where the charges are inside it, the total flux through the surface is simply proportional to the total charge inside, the net charge inside. And it's equal to the net charge either times this 4 pi k or divided by epsilon naught, regardless of the size. And it's a very powerful thing. It's kind of hard to understand that you can draw, you can wrap any size or shape of wrapper around this collection of charge, the same total flux through it. But it's true. Proving it is beyond us right now, and you probably don't care about proving it right now because you're cared about a quiz on Monday. But that's the gist of it, and I will show you a couple uses of it in the next two videos.